Welcome back. Today we're going to talk about statistical hypotheses, and this is a very subtle and nuanced topic, and so we're going to take it slowly, and we're going to do a lot of examples. So what is a statistical hypothesis? A statistical hypothesis is simply a clear and testable statement of some difference or effect. It could be almost any kind of statement that can be measured. It can be something that we basically know or something that's really a mystery. And I've got some examples here of some statistical hypotheses for us to talk about. The first is that hydroxychloroquine is a useful treatment for COVID-19. This is a testable hypothesis. We don't know whether it's true. The second is that global temperatures are rising. This is a testable hypothesis too. It's very clearly known. The third is from an example that we're going to study in detail, and that is that we have a statement: certain managers will show bias against women in promotion decisions. We're going to deal with a study from the 70s in which we have some data on this, and we're going to do what we call a hypothesis test about this. The next one is kind of frivolous. Dogs are smarter than cats. This is a arguably not clear. I mean, it's testable, but it's not clear exactly what it means to be smarter. And there are various interpretations of that. So this is arguably not quite clear enough to be a true statistical hypothesis. The next is from the topic of quality control. If you have a machine, say in a factory that's producing parts, then you might suspect or want to test whether it's producing parts that are appropriate. And so you might hypothesize that it's producing parts that are larger or smaller than the specification. And then you would need to know the answer to that. You would need to collect some data and find out whether that was true or false, because it would affect the product that was being produced. And the last is just an efficacy question. Ammonium nitrate fertilizer will improve my tomato yield. Maybe it will, maybe it won't. That's a common fertilizer. This is certainly a testable hypothesis. Now, something that I want to remind you of that we've talked about before, but I can't overemphasize, is the basic notion that parameters are not statistics, and the basic distinction between parameters and statistics, which follows the basic distinction between the population under study and the sample, which is the actual collection from which we draw our data. So in every one of these situations, we can imagine some great population of everything, some population of all the dogs and all of the cats. And then we could imagine some which we sample, right? Certain 20 people's pets, for example, and that would be the sample. Now, the sample is the collection that we know a lot of information about because we collect the data from them. The population is supposed to be modeled by the sample, but we don't directly know what's going on in the population. We haven't directly measured them. If we had, they would be part of the sample. So something like global temperatures are rising, we don't have information about every location and every time throughout all of history, but we have a lot of information. The information that we have about global temperatures, which is both location and time information, that information forms our sample. The rest of the information about how warm it was on a certain place in a certain time when nobody took the trouble to write it down, that is sort of the rest of the population. And the population is, in most cases, far, far larger than the sample. With a political polling situation, the population might be the population of the United States. The sample might be a few people that we called. It is from the sample that we pull the data, and we typically get a data frame here with variable names, and each row represents a case here. So we pull the data frame from the sample, and then we describe it, and when we describe it, then we get the mean, we get the standard deviation, we get other information, and these pieces of information, which are descriptions of the sample itself, those are statistics. The average among the sample is a statistic. The standard deviation among the sample is a statistic. The min and max, median of the sample, these are statistics because they describe the sample, but there are corresponding values about the entire population. The mean of the entire population is a parameter. It's notated mu, not x bar. So here, notice the statistic is x bar, the parameter is mu. Now we take for granted that mu and x bar are likely to be similar. They're probably approximately the same value, but they are not necessarily equal to each other, and distinguishing them is probably the most important basic concept in statistics. We also have parameter and statistic notions of the proportion here. We typically use the symbol p for a proportion. Say the proportion of women recommended for promotion versus the proportion of men recommended for promotion. Those proportions could be viewed in the entire population, which would be some sort of hypothetical population, or they can be viewed in the sample itself. If they are parameters and describe the population, we write P. If they are statistics and describe the sample, we write P hat. Another case where we would be measuring these things by proportion would be in recovery rates based on some treatment or based on the control group. Then we would have a proportion for an experimental group and a proportion in a control group, and that would all describe the sample, but we would want to make inferences out into the population. That's really the important thing, so that we can say something more general, and those generalizations are called inferences. And being able to do that correctly without just jumping to conclusions based on small samples is really the responsibility of careful and correct hypothesis testing. Now, these are clear hypotheses. They describe measurable differences, but they're not phrased in terms of statistics, and they're not phrased in terms of parameters either. And so, although these are clear ideas in need of testing, I'd like to do an example here where we take one of these and we pull out the actual statistics of it, but actually it won't be the statistics, it's the parameters that are really being addressed here. So we're going to take this example, which we'll return to, this managerial bias example, and we're going to sort of translate this into a language that indicates that we really are talking parameters here. So this is from a study that we'll get to the details later, but the idea is that we have some managers under study, and we suspect that they might be showing gender bias against women. And so we give them some files to evaluate for promotion. And what happened in the study was that they recommended for promotion the men more than the women, which you might suspect there are lots of reasons for that, but they weren't really men, they weren't really women, they were just tagged that way. And so that seems to indicate that the managers are showing some sort of bias in that study. The bias is a reference to a difference, and we need to be really clear here. What is different? So here we have actually 4 different proportions to talk about, and I'm going to start naming them. They are P hat for the women, P hat for the men, P for the women, and P for the men. So this is the proportion of women. The P hat for the women is the proportion of women recommended for promotion. And because it's P hat, which is a statistic, not a parameter, then that's in the sample. And this thing, P hat for the men, is of course going to be the proportion of men promoted or recommended for promotion in the sample. These statistics also have corresponding parameter versions, which is the population-wide version of the same thing. So the P for the women would be the proportion of women. And this is sort of hypothetically because they weren't actually asked to do this, but hypothetically the proportion that would be promoted. And this is the question population-wide. And this is the P for the men is going to be the proportion of the men recommended for promotion, and again, population-wide. So one simple question, will the managers promote the women more than the men? 4 proportions that are relevant here. Now, these 2 over here, as I mentioned, these are stats. These are not stats. These are parameters. And here we see, again, the basic conflict of statistics, which is what you're measuring is not exactly what you want to talk about. These proportions of women generally and men generally in the population that would be promoted, these are better reflections of whether these managers are actually biased. These statistics are just about the certain 48 files that these managers read. And there may be coincidences or errors within those certain 48 files that and 48 is not a very large number. This is less interesting information because it's specifically about these certain files. This is more interesting information because it's about population-wide, it's about the general trends. And so this is really what we are interested in. But the basic problem of statistics, this is what we measure. We don't see the entire population. We don't see what these managers would do population-wide. What we see is how these managers have actually behaved on this particular randomized sample of 48 files. Nevertheless, the hypothesis here, they will show bias, is a hypothesis about the parameters. And this is really key here. This is going to be true for all of the hypotheses that we're going to be looking at here, that the hypothesis is basically the statement that P for the women is less than P for the men. The hypothesis is a statement of inequality, and it's an inequality between the proportion of women that would be recommended for promotion and the proportion of men that would be recommended for promotion. So this reformulation allows us to say very, very precisely what we mean when we say that managers will show bias against the women. So this is an inequality, a statement of inequality using parameters. Now, obviously, the statistics are going to be involved. The only way we can use our data is to involve our statistics, right? We've taken 48 data points, and we can calculate p hat w, and we can calculate p hat m. But the only way we can actually use our data is to use these statistics. So we will have to use that, and we will have to refer to these things too. But the hypothesis is phrased in terms of the parameters themselves, and we'll see that as a general trend. And so hypotheses will have letters like mu in them, but they will not have letters like x bar in them because those are references to our data. Hypotheses are generalizable statements. So let's look at the other example, that the machine is producing parts that are larger than specification. So I've erased that, but let's clear this board and talk about that, because there we're not dealing with a proportion at all. We're dealing with an average size of the resulting parts. And so the hypothesis will take a different form. The other reason this hypothesis will take a different form is that we're comparing against specification, which we presume is some single fixed value. Instead of comparing, men versus women, we're just comparing the average part size to some particular value, some specification. So when we deal with the statement, the machine produces parts which are larger than specification, this can be translated into a statement about parameters and statistics. And so the statistic of interest is going to be x bar, which is an average, right? An average within sample, that's a statistic. So the x bar, which is going to be the average part size. So, I mean, if you're really interested in quality control, the average part size is obviously not the only thing that you would worry about. You would also worry about how much variability there is among them. But this is just a simple example here. So the average part size would be the relevant statistic, and the corresponding parameter would be the value mu, which is the average part size. Again, they're both average part size, but this one will be population-wide. So what is the population in a quality control setting? If you're talking about a machine, which is part of a factory production process, the population would be all of the parts that it produces. The sample would be like, for a few days in a row, you go in and you take some parts off of the machine and you just measure those, right? You're not measuring everything. Most of these things are getting shipped off, but you're going to take out a few and measure a few, and that will form the sample. And so you're going to take the average part size within the sample. So typically we don't have the luxury of literally measuring every single part that would come off of a machine, depending on what it's doing, of course. So what is the hypothesis saying? The hypothesis is saying that the average is too big, but which average? What's really relevant here? if we go in on a Tuesday and go in later on a Thursday and go in later on a Saturday and we measure 10 parts each day and we end up with 30 measurements, then the statistic is the X bar. That's the average among those 30 particular parts. We don't exactly care about those 30 particular parts. We're using them as a measurement to see what the machine is doing. But what we actually care about here is the generalized average of all of the parts. And so if the machine is misbehaving or not, that's really commentary about mu, about how these parts, all of them that come off the machine, are behaving, not about the specific 30 that we measured. So even though this is how we will gain our data and gain our insight into what the machine is doing, the hypothesis that we're making, that the machine actually produces parts which are off spec, that hypothesis is a statement about mu, not a statement about X bar. And the hypothesis, which I'm writing HA again, the hypothesis that we're making is going to be something like mu is greater than 10. And I'm just making up this number 10. Whatever the right value is, right? Maybe it's supposed to produce parts that are 10 centimeters or something. Mu is going to be greater than that particular fixed value. And you might think, you know, how hard can it be for a mathematician to figure out whether mu is greater than 10? And like, how could there be any challenge here to assessing whether a given number is greater than 10, right? You average these measurements together and you figure out whether it's greater than 10. But wait a minute, it's not quite that simple. And that's why statistics is hard. So when we collect a whole bunch of parts off of this machine and measure them, then we get an average, but that average is X bar. And it'll be really easy to tell whether X bar is greater than 10 because we can do df.describe or whatever, just calculate the average. We can easily figure out what X bar is after we've measured some parts. But X bar and mu are not guaranteed to be the same. And if X bar is 10.5, well, depending on how this machine works, mu could be 10. It could just be a coincidence or something that X bar was just a little bit off. So in fact, we expect X bar to be a little bit off from mu, but until we can predict how much off we expect it to be or what are the probability of getting certain errors, then we don't know by looking at X bar whether mu is greater than 10. You see, the subtlety, the nuance here comes from the fact that mu is invisible to us. It describes this population-wide thing, which is happening out there in the population, but is unmeasured. X bar is what's visible, and we expect X bar to be close to mu, but unless we can precisely describe how close, then we won't be able to resolve this hypothesis. The goal of hypothesis testing is to decide whether we should believe this. And we need some statistics to do it. All right, one more example. The ammonium nitrate thing. Ammonium nitrate is supposed to increase my tomato yield. So let's deal with the structure of that hypothesis. So how do we phrase that in terms of statistics and parameters? So let's write down the hypothesis. So the hypothesis is that ammonium nitrate will increase my tomato yield if I use it as a fertilizer in the garden, okay? Who knows? This is a testable hypothesis. If it's a fertilizer, you might expect that it will, but I don't know, maybe it doesn't work for tomatoes. So now here, it's not clear. Is this a proportion problem? Is this average? What are the basic quantities that we're dealing with here? This is a question about tomato yield, and tomato yield would probably be expressed as maybe an average, maybe the average bulk of the harvest from each plant. And so let's just say, for the sake of argument, that X bar is the average yield among plants sampled. And then mu would be the average yield among all tomato plants. And this is kind of theoretical here, right? Like all tomato plants under all conditions, even growing in the desert. Really what we mean here is all tomato plants growing under similar conditions or something. So there's a little bit of ambiguity in how broad the population will be here. But that's not enough, because each of these averages so this is the average for the sample, and this is the average for the population, but each of these averages needs to be refined, because this hypothesis is actually is actually a comparison. It's a sort of a what if hypothesis. It's a comparison between what would happen with the ammonium nitrate and what would happen without the ammonium nitrate. And so it's not enough. We don't really just have two averages here. We have an average among those sampled if I don't use the fertilizer, and then we have an average among those sampled if I do use the fertilizer. So let's call these the control. I'll subscript them with a C for control, and I'll say no ammonium nitrate. And then here, this is also if I use no ammonium nitrate here. And then I also have an experimental version of each of the same. So the experimental average, so this would be the average yield among sample. And that's if I do use ammonium nitrate. No need for placebo here because the tomato plants don't know whether they've been treated. And this is the average yield generally, and that's with the ammonium nitrate. So there are really four averages going on. There's the distinction of whether we're doing an average in sample versus whether we're doing the average in the population. And that's the X bar versus mu distinction. And then there's a distinction of whether we're doing average with the ammonium nitrate or without the ammonium nitrate. And that's the control versus experimental decision. How do we express the hypothesis in terms of these numbers? Well, again, the hypothesis isn't a specific statement about the 5 plants that I actually bothered measuring here. The hypothesis is supposed to be a generalized statement about what would happen to tomato plants generally. And so the hypothesis does not address the statistics, X bar. The hypothesis addresses the parameters, mu. And here, the hypothesis is an inequality between the mu for the control group and the mu for the experimental group. This is the average yield among the experimental group, which is treated with the fertilizer. And this is the average yield among the control group, which is not treated with the fertilizer. And the hypothesis should be a statement which declares which of these is bigger. And I'll give you a minute to think about which one you think is bigger. It should probably be this one. And so the inequality goes this way. So just a tip reminder from grade school, the inequality point, it directs itself in the direction of the larger, it likes to eat the larger quantity. So, so the inequality is stated this way. So this is how we take relatively imprecise but human readable versions of our hypotheses, and we express them as inequalities among parameters. And this is the general theme, that hypotheses are talking about parameters and they are stating inequalities. Anytime we're stating an effect, we're stating that something is greater than something else or something is less than something else. Sometimes we're describing an average, like the average tomato plant yield. Sometimes we're describing a proportion, like the proportion of women promoted or the proportion of men promoted or the proportion of, you know, whatever population that votes Republican or Democrat. Sometimes we're describing proportions, sometimes we're describing averages, but in every case, we're describing population-wide what's going on when we're talking about our hypotheses. That's what gives this whole business some complexity, because it's easy to take a little bit of data and then you know the value of X bar C and you know the value of X bar E, and then you can compare them, and it's easy to compare them and you can say, well, that's the one that's bigger. The question is that strong evidence or is it not strong evidence that the actual parameters attached to those things are also going to have that same relationship? To state that in a simpler language about tomatoes, supposing I go out and I actually carefully garden and I put 5 tomato plants in my control group and 5 in the experimental group, and then I happen to notice a difference of yields, right? Well, 5 and 5 is a really small sample, and you could certainly argue that that difference in yields, especially if it's a small difference, is not evidence that the fertilizer was a big deal. It's evidence that that the plants just kind of got lucky, that it just, the numbers fell that way, just sort of accidentally. And so even if there is a relationship between the measured values, you have to question, is that strong evidence that there is a relationship between the parameters? Or is it just a coincidence of the numbers because of small sampling? And this is where statistics really gets complicated. All right. So the symbols that we're going to use, I want to remind you, are mu and p, and we'll use those for describing these parameters. So I've used this symbol again and again here, HA, and I want to talk to you about why I'm calling this HA. It's because of a kind of an unfortunate name for the main clear and testable statement or difference or effect, the main hypothesis in any scientific or statistical study. So I think I'm going to erase this, and then I'm going to explain why I keep calling these hypotheses HA. So HA stands for alternative hypothesis. I'm not a big fan of the name because in any scientific study, there's a main working hypothesis that you're trying to study, trying to figure out whether it's true. And HA stands for that main working hypothesis. The treatment is working, the managers are biased, whatever that main working hypothesis is, that's called the alternative hypothesis. The word alternative is somewhat confusing because it sounds like it's secondary, and there's another one that's like the main one. HA is the main one. The alternative hypothesis is the main one. There may be competing hypotheses, and we'll talk about that. We'll talk about that soon. So when we talk about HA is the symbolism of it, the fact that it's a capital A and it has a subscript and it looks all mathematical, that suggests that it has some sort of mathematics to it, and it does. I don't want you to think that HA is a number. HA is not a number, it is a statement, right? The statement like the production line is producing parts that are wrong, or the statement that this mu is less than this mu. The HA is a claim or statement, and it needs to be true. It could be true, it could be false. In most cases, as we begin the study, it's unknown, and at the end of the study, hopefully, we know whether it's true or false. All right. So there are, you may have noticed here that as I've gone through these examples of hypotheses, there are several different types of hypotheses, and I want to add some language to describe what are the kinds or structures of the various hypotheses. So types of hypotheses. So what are the various formulations of a hypothesis here? So we can have, the first type is we can have a comparison to a fixed value. So an example of this was when we were talking about the machine producing parts with an average which was compared to 10. So the hypothesis was that the average was greater than 10. So we're comparing against a fixed value. So the alternative to this is the comparison between two measured values. The managerial bias was a case like this. We had the proportion of women that were promoted and the proportion of men that were promoted. And the central question was not about how likely are managers to promote men or women or people generally. The central question was about the relationship between those two proportions. So it doesn't really matter whether they're promoting 90% of people on average or 10% of people on average or 50% of people on average. We don't really care about the actual values there. What we care about is their relationship to one another. And so that's a hypothesis that compares two measured values. If we have a hypothesis like, I don't know, tigers are bigger than lions. So this is probably a hypothesis about the average mass of a tiger in relation to the average mass of a lion. And the hypothesis is a comparison. To assess whether tigers are bigger than lions, you don't actually need to know how big they are. I mean, absolutely, you don't need to know the average mass of one or the average mass of the other, except that we are trying to compare them to each other. So this is when we would compare two measured values. Why is this different from comparison to a fixed value? At least when you're comparing to a fixed value, you know what the fixed value is, right? You're comparing to 10 and you know you're comparing to 10. If you measure the average mass of a tiger, by a statistic, you still don't know the parameter version of the average mass of a tiger. So comparing two parameters to each other is particularly difficult because you don't exactly know either of them. And so we have a lot of tests that are designed to overcome this basic problem. So, so we also have one-sided hypotheses and two-sided hypotheses. And this is a very important distinction that we are going to have to attend to, and it's going to make a difference when we calculate our p-values, what we do with those p-values. So often, let's go back to the quality control example. Often if you're assessing a machine and you're trying to see whether it does obey the spec or not, whether it's producing parts that are the right size or not, often you don't really care whether they are too large or too small. So often the quality control hypothesis might be something like the parts are not the right size, right? Too large or too small, I don't care. Anything not the right size is significant and requires action. So that would be a two-sided hypothesis. This is a comparison stating inequality. What's a one-sided hypothesis? A one-sided hypothesis is a comparison with direction. So it states that something is less than something or that something is greater than something, and it specifically says what. So a one-sided hypothesis might be something like the managers are biased against the women. So against the women clarifies that we're claiming this proportion is specifically less than that proportion, right? So it's one-sided in the sense that it states a difference and it communicates the directionality of that difference. So if I say lions are bigger, well, I suppose they would be small. Lions are smaller than tigers. Then I'm stating the difference, but I'm also stating which one is smaller, right? That's a one-sided hypothesis. If I simply say, on the contrary, lions and tigers do not have the same average mass, just not the same. Maybe one of them is on average bigger, or maybe the other one is on average bigger. If I simply say they have different average mass, then that's a two-sided hypothesis. Now, notice that these things can kind of be combined in lots of combinations. You can compare to a fixed value, but with a two-sided hypothesis, like in the quality control situation. Or you can compare to a fixed value with a one-sided hypothesis. Or you can compare between two measured values with one-sided or two-sided hypotheses as well. So these things can be combined in interesting ways. So, so we need to watch for the various types of our hypotheses, and we need to attend to what kind of hypothesis it is, because often it will influence the exact choice of what testing we use and how we treat our p-values later. As we haven't talked about p-values, but what we do with them later will be affected. Okay. So we've talked about what the alternative hypothesis is, and we've got a symbol HA for the alternative hypothesis. And the alternative hypothesis is the main working hypothesis that usually we're trying to prove. If there is only one hypothesis, then, well, I guess we have no choice but to believe it. But that's not how science works, right? When you have a main working hypothesis, then you probably have a competing theory. And so I want to talk to you next about how we write and how we identify the competing theories for our hypotheses. So one-sided hypotheses have opposites and null hypotheses. So statisticians usually don't talk about opposite hypotheses very much, but I think it helps to clarify the relationship between the alternative hypothesis and the null hypothesis to also think about the opposite hypothesis. So let's take the fertilizer example. The simplest way to phrase the fertilizer example is to say something like fertilizer will increase yield. So in the context of what we said before, one-sided versus two-sided, one sample versus two sample, this is a one-sided hypothesis. It states difference and it states the directionality of the difference. It says the fertilizer is going to do something and it's going to be positive. It's a comparison between two means, effectively, because we've got the yield in the control group and we've got the yield in the experimental group. And this hypothesis is ultimately saying that the yield in the experimental group is going to be bigger than the yield in the control group. And so this is a comparison between two parameters, but it's a one-sided comparison because it specifies the directionality. So that means that it's appropriate. These are about one-sided hypotheses. So if we're saying the fertilizer will increase the yield, then that's a plausible point. That's a testable statement. If we're going to test this in an authentic way, then we have to at least be willing to entertain a counterpoint. So what is the counterpoint to this? Well, actually, there are two different kinds of counterpoint to this thing, and we're going to give them technical names so that we can talk about this. So the first counterpoint that you might imagine is fertilizer will decrease the yield. This is certainly a counterpoint, and this is certainly plausible, right? Because like a given fertilizer affects a given plant in a certain way, and it might be the wrong kind of thing to choose if you want a better yield. So this is a plausible counterpoint. But there's another and different counterpoint, and that is that fertilizer will have no effect on the yield. Maybe the chemical is just irrelevant. Maybe it doesn't make any difference. And so these are both counterpoint to the alternative hypothesis that the fertilizer will increase the yield. And these are counterpoints that I want to give names to. This one we will call H subscript op for opposite. This is the opposite hypothesis. It's a counterpoint that says, no, you've got it backwards, it's the other way around. This, which is perhaps more important statistically, this is a counterpoint that we will call H subscript 0, and that is what we will call the null hypothesis. So this one is the opposite hypothesis. It states the opposite directionality of difference. This one is, we will call this the null hypothesis. It's a statement of no effect. It doesn't matter. So in the managerial bias case, there is a clear opposite hypothesis and there is a clear null hypothesis too. In that case, the original alternative hypothesis states that the managers are biased against the women in favor of the men. A counterpoint to that might be the statement, the managers are biased against the men in favor of the women. That would be the opposite hypothesis, right? Because it reverses the directionality of the bias. But then there is also an important hypothesis that states probably what we hope, the managers are unbiased, right? The managers have no bias in favor of the women or in favor of the men. So that would be the null hypothesis. It's a statement of no effect at all. So notice that the opposite hypothesis and the null hypothesis are both counterpoint to the alternative hypothesis, but they are not the same counterpoint. And so what often happens is we need to be able to identify the alternative hypothesis, and from it, we need to figure out what would be the statement of the null hypothesis or opposite hypothesis. The opposite is obtained by reversal, and the null is obtained by sort of saying, no, 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 there's nothing going on here, there's nothing to see here. So let's look at the slightly more frivolous example. Dogs are smarter than cats. This also has an opposite and a null version, and you can probably figure out what they are. So I'll just write it quickly. Dogs are smarter than cats. This is a plausible alternative hypothesis. Arguably, it's not really scientific because smarter is kind of ambiguous here. You might, but then again, maybe you could design some experiments to say this is what we mean by smarter. In any event, dogs are smarter than cats. What's the opposite statement? It's very clear. Cats are smarter than dogs. Or you could say dogs are dumber than cats, I suppose. Cats are smarter than dogs. So that would be the opposite hypothesis. Cats are smarter than dogs. It's the counterpoint to the alternative hypothesis obtained by switching it around backwards and saying it the other way. And the null hypothesis is probably more interesting for statistical purposes. The null hypothesis says Cats and dogs are equally smart. Whatever it is we actually mean by smart, which is kind of ambiguous in this example. So cats and dogs are equally smart. Um, the null hypothesis is a statement of parity or equality. And so these are the relationship between the three competing hypotheses. The job of hypothesis testing is to inform the procedure that helps us figure out, well, which of these do we actually believe, right? We're going to collect some data, and then we need to decide which one we're actually going to believe. And, or whether we're just not going to really commit. Like maybe you collect some data, there has to be some time when you say, well, you know, the data is inconclusive. So when is the data inconclusive? And when is the data really conclusive? When do we have statistically significant results, and when do we have statistically insignificant results? These are deep questions that we'll get to. Last example that I think I won't write is a drug efficacy question. If you say something like beta blockers lower blood pressure, then you could have an opposite hypothesis, which would be something like beta blockers raise blood pressure, or you could have a null hypothesis, which would be something like beta blockers have no effect on blood pressure. So these are the various hypotheses that match. Now, that match against a one-sided hypothesis. Now, what if the hypothesis is two-sided? So a two-sided hypothesis might be something like, these managers are biased, just biased. They're biased in favor of somebody. I'm not saying who, but they're biased in favor of somebody. Or it might say something like, lions and tigers have unequal average mass. Well, that doesn't really have a clear opposite. In a way, it is its own opposite because it's stating that there is a difference, but it's not stating the directionality of the difference. And so there's no way to reverse the directionality of the difference. And so two-sided hypotheses have no opposites, or I suppose in another way, they are their own opposites, but they still have null hypotheses. So for example, if the alternative hypothesis is managers are biased. Now, notice I'm not saying in favor of the men, in favor of the women. I'm not, just biased in favor of some gender discrimination is going on, but I'm not saying which way. Then I can't opposite that, right? It doesn't change. But I can still say that there is a null hypothesis, and the null hypothesis is the statement of parity or equality here. And the simplest way to say that is to simply say managers are unbiased. If the alternative hypothesis is my juggling skill has changed over the last year, then the null, so notice this is a two-sided hypothesis because it says has changed. If we can measure skill numerically, then this means it has increased or it has decreased, but this is being ambiguous about whether it has increased or decreased. It's just saying there is some measurable change. The null hypothesis should state no effect. So in this case, that would mean my skill is unchanged. So the null hypothesis is the changed, well, is the modified statement that states there is no difference, there is no effect, don't worry about it. Okay. So the hypothesis test is designed to figure out which one of these we should ultimately accept. And if the alternative hypothesis is the one that we ultimately suspect that we are trying to prove perhaps, then our agenda should be to use some kind of logic to rule out the null hypothesis. And that has a special fancy name in statistics. We say that we are rejecting the null hypothesis. Basically what we're doing here is we're saying, I have a main theory, which I'm calling the alternative hypothesis, and I'm going to set that theory into a contest with a counterpoint, and the counterpoint is going to be the null hypothesis. And so now I have this contest between two theories. The alternative hypothesis is one version of truth, and the null hypothesis is another version of truth, and I have to establish which of these is true, which of these is the right explanation. Now, if I'm setting them up against each other, then I probably suspect that the alternative hypothesis is true, and then I'm going to collect a bunch of data and do a bunch of math, and then ultimately what we hope, or what we expect, is that the null hypothesis is not credible after all of that data collection and math is performed, right? we do a whole bunch of data collection, and we see it's not credible given the data that we're looking at that the managers are unbiased. And that is called rejection of the null hypothesis. So we'll talk about that more later. So what is the basic structure of hypothesis testing? We set these things up against each other, and then we figure out which one wins. So the steps of a basic hypothesis test is first we identify what is the alternative hypothesis. This is our main working theory that we are attempting to prove, and we have to know what we're trying to prove, otherwise we won't have much luck proving it. The next thing that we do is we identify the counterpoint, which is the statement of no effect or null hypothesis H0. That's the null hypothesis, and that's the competing theory. Next, we're going to collect the data, and the data is going to inform our decision. And then, based on the data, we're going to calculate, well, can we calculate the parameters? Well, no. The hypothesis is phrased in terms of the parameters, but we can't calculate the parameters because we have the data from the sample, but we probably don't have the data from the entire population. And so we're only going to calculate the statistics, which is the best that anybody can do. And then the key question is our data compatible with the null hypothesis? Basically, we're measuring whether the data is compatible or incompatible with the null hypothesis. So if the answer is yes, what does that mean? So if the answer to this question is yes, then that means that, well, maybe nothing is going on, right? That means that the data that we collected is totally realistic if indeed nothing is going on. So maybe we ask the managers to review a bunch of files, and the data that we get back is completely consistent with the hypothesis that they are completely unbiased. And then we say, oh, well, I mean, that's probably good news, right? It seems that the managers are unbiased. If we're collecting data about, you know, whether the fertilizer is effective when we're gardening, then the question is the data that we gathered consistent with the null hypothesis? What's the null hypothesis in that case? The null hypothesis is the hypothesis that the fertilizer is useless. It has no effect at all on the plants. It doesn't increase, it doesn't decrease. If the data is compatible with that, then we're like, well, I guess it probably didn't work. And so now maybe it worked a little, but it didn't work enough to be really conclusive. And so if the answer is yes, then actually both theories are potentially credible. So just because the data is compatible with the null hypothesis doesn't mean that it's incompatible with the alternative hypothesis. And so both theories are credible. And the answer is we don't know. Now, if this is disappointing, well, it should be, right? It is disappointing when you do a whole bunch of work and your statistics point you to the conclusion that you don't know. But let me remind you that if science has any integrity at all, then it has to be capable of saying, I don't know, right? Somebody who always knows the answer is a liar, right? If we're being responsible, then under certain conditions, we won't know the answer. And these are the conditions under which we will say, gosh, I just don't know. And we will admit our ignorance. We don't know because the data may be compatible with the null hypothesis. It may be compatible with the alternative hypothesis. I really don't have any reason to say, gosh, I know which one of these hypotheses is right. But there is another case here, if no. So again, this is if no to this question. Is the data compatible with the null hypothesis? So if the data is not compatible with the null hypothesis, then what that means is we just formulated two hypotheses, an alternative hypothesis, which is our main theory, a null hypothesis, which is our counterpoint. We collected a bunch of data and saw that the data is out of whack with the alternative with the null hypothesis H0. And if the null hypothesis is incompatible with the data and the data is real, then that null hypothesis must be the wrong theory. So we reject the null hypothesis. Now, when we reject the null hypothesis, well, then there's only one hypothesis left, and that is the alternative hypothesis. This is what we want to do. We want to declare that the alternative hypothesis is true to statistical significance, right? So we declare that the alternative hypothesis is true once we reject the null hypothesis because we've eliminated the counterpoint to it. And that's good. That means we know the answer. And then we publish. Notice in an ideal world, we publish in both situations, right? There is a bit of a problem with our publication culture, which is that we tend to only publish in this case. And so a lot of these negative results are invisible. Ideally, we would publish in every case so that we would share all of the knowledge. And then at least if somebody's done it and realized that this study didn't work, then at least we should know that this study didn't work. And so we should not repeat it at least. That's at least a simple reason why we should publish. These are our negative results and these are our positive results. So that's the basic structure of hypothesis testing. We identify the alternative, we identify the null, which is a counterpoint. We collect our data and calculate our statistics, and notice we only calculate statistics because that's all we can calculate. And then we ask this key question, which is, there's a bit of mystery still left in this question. Is that data compatible with my null hypothesis? And then we actually hope that it's not, because the null hypothesis is our counterpoint to our main suspicion. We hope that it's not compatible with the null hypothesis, and we reject the null hypothesis. We declare this one true and we publish. So this is the ideal outcome of a successful study, and this is the ideal outcome of an inconclusive study, that both theories remain potentially credible, and maybe we have some preliminary evidence or something, but we need to do more study in order to have statistical significance. So this is the basic structure of statistical hypotheses and how we use them. What we need to do going forward is figure out how on earth we're going to answer this question in practice, because this is the key question, right? How do I look at the data and say, is it or isn't it compatible with some hypothesis that there's no effect at all? And so maybe the data shows a little bit of trend in one direction, but it's not very strong, and the data set is kind of a small size. So I want to sort of make a judgment about this, but how do we make those judgments, and on the grounds of what mathematics? That's what we need to get into next. All right, thank you.